Okay, so hello and welcome back. So in this video, normally what we would do, or we should do, is basically go through basically chapter 15 or chapter 16 of class 11, which is probability. Now, the problem is that we do need to go back a little bit and read. There are some basics and some definitions related to probability that we need to know, and so we need to go back and take a look at those things. So what I'm going to do, I suppose this thing actually starts at, so I've come back all the way up to class 9 and take a look at class 8. Let me see what we have over here. 16, no. 15, no. 14, somewhere over here we must have some chapter related to probability. So it's linear equations, practical geometry, comparing quantities, insulation. Well, surprisingly enough, there is no probability in here for in class 8. So you have practical data handling. Maybe it's been a part of some other chapter. And okay. So there is no probability in class 8. In class 7 we had now, you know what happens is that in class 7 and 8, so the basically the first place where, so we have the class 7 and 8, there is no probability, and there is 9, 10, 11, which we have already over here. So 9, 10 and 11. Okay, so what happens is that in class 7, for example, if you take a look at the books, you will not find a chapter called probability in class 7 or in class 8. Anywhere you go, you would not find a chapter called probability. In these books, probability was still not discussed as a topic of its own, or as a standard topic, as a standard basically topic discussed here. In turn, it was, for example, a part of statistics, and statistics in these books still didn't have any name, meaning that, for example, it was called data handling and something like that. And basically the material that you find in these books in class 7 and 8, then of course they have been migrating the same material to class 9 and 10 and 11, and then of course 11 is a little bit more advanced, but then class 9 and 10. In class 9 it gets a little more rigorous, and in class 10, as I remember, there is they start to give you definitions related to probability and that sort of thing. So what I'm going to do is that I'm going to start with class 9, but I'm not going to get into the chapter basically solving all the examples and all the exercises and everything. I'm going to basically review the chapter related to class 9, whatever the important concept we find over there, we will talk about it. and then I will do the same thing for chapter 10. For chapter 10, I'm going to go over the important material, and and once we have covered the important material and the definitions here, then we will get to class 11, which is class 11 probability, which is what we want to discuss now. So let's start with class 9 then. And this is just, remember, just a review. The main thing that I really want to do here is basically the main thing that I want to do here is probability chapter 16 class 11, but then for that we need to do some review basically. So for now, what we want to discuss is a review of probability actually probability is supposed to be written this way: probability, that is basically class 9. And you would see it this way basically in the book, or this way, class 9. Okay, so I will just simply go through the text. Wherever I see there is something important, we will talk about it and we will get through the chapter. So it says that, as an introduction, it says that in everyday life we come across statements such as "it will probably rain today," or "I doubt that he will pass the test," or "most probably Kavita will stand first in the annual examination," or "chances are high that the prices of diesel will go up. There is 50-50 chance of India winning a toss in today's match." Now the words probably, doubt, most probably, chances, etc. used in the statements above involve an element of uncertainty. For example, in the first sentence we said that we probably rain will mean that it may rain or may not rain today, meaning that we are predicting rain today based on our past experience when it rained under similar conditions. Now, similar predictions are also made in other cases listed in the other basically sentences that we had here. So the uncertainty of probability of the uncertainty of probably, or the other words that we use in those sentences, can be measured numerically by means of probability in many cases. So basically we use the words, for example, probably, we use the words probably, we use the word doubt, we use the word, for example, the phrase most probably, we use the word, for example, chances are high, for example, and so on and so forth. And there is a, for example, there is a 50-50 chance that, and so on and so forth. So these words, probably, doubt, most probably, chances are, or basically there is a 50-50 chance, and so on and so forth. Now we can measure the uncertainty of these words numerically by means of probability. So what that means is that we can use the concept of probability in mathematics to measure the uncertainty linked with these words, and we can then express those uncertainties in terms of numbers. That's basically what probability is, which is actually a very interesting topic in mathematics. And now that I think about it, it's actually a very interesting topic generally, because if you could actually, for example, based on different situations, if you could link for example, if you could link a numerical value to the uncertainty linked to some event happening or not happening, for example, then of course it would help you do a whole bunch of things. For example, suppose that a weather station or a weather report station or a weather forecast station. If you go to a weather forecast station, it tells you that there is, for example, 20% chance. There is a 20% chance that it will rain today, or there is a 20% chance that this is going to happen, or that is going to happen, or there is a 30% chance that basically something else is going to happen. And so now what they have done, they have actually found a way, based on some procedures and based on the past experiences and based on the data that they had before, to come up with, for example, some numerical value, which is nothing but a number, but this number, we can actually do a whole bunch of things with that. They have found a way to come up with a number, and you can actually count on that number, meaning that, for example, based on the number that you read on a weather forecast station, for example, that there is, for example, 50% chance that it's going to rain today, you actually take a raincoat with you, and most of the time, I would say, I couldn't give you a number, but probably even up to 90% of the time, your predictions based on those numbers are actually true. So that's the beauty of the whole concept of probability. So, and of course, it's actually impossible to do anything in mathematics, or do anything, for example, in physics or in any other branches of science, if you don't understand the concept of probability, because then when you get into science, it's not like, for example, you could say that things are not decided, are not straightforward. There is always basically a probability of this happening or that happening, or that not happening, and so on and so forth. And so science is always based on this concept of probability. So with that in mind, so let's now try to understand probability so that we can use it in science. Okay, so now let's see what we have here. Now it says that though probability started with gambling, it's been used extensively in the fields of physical sciences, commerce, biological sciences, medical sciences, weather forecasting, etc. So as I mentioned, of course, I'm in no way an expert in probability or anything like that. But I know that, for example, when you get into higher physics or higher mathematics or wherever you go in sciences, you do need probability. Otherwise, meaning that you do need to have a way to deal with uncertainty, because the problem is that everything is uncertain. So if you don't have a way to deal with uncertainty, then you cannot really move forward. That's the problem. And basically probability solves that problem. Now, one thing that I forgot to say is that this is right now 9, 10, and 11. So this is class 9. This is probability class 9. And if you have read these NCERT books in class, for example, in class 7 or in class 8, the concept of probability was informally introduced in basically in the chapter which was related to statistics. And of course over there we had no statistics, no formal statistics. The statistics was also dealt with informally as data handling, for example. So an informal way to refer to data handling would be statistics, and then basically probability was a part of this chapter. And of course, as you can imagine, probability is very strongly linked with data handling, because once you create some concepts, once you develop some concepts to deal with uncertainty, then of course then you need some way to handle your data, put your numbers together, and basically get answers out of your, basically somehow to deal with those numbers. And the way to deal with numbers is of course the statistics. So you might, if you want to understand probability, of course you do need to understand the statistics as well. So that's basically that. Now, the next part that we have here has been called probability and experimental approach. 427. The next part that we have over here is probability and experimental approach. So let's see what we have here. It says that in earlier classes you have had a glimpse of probability when you have performed experiments like tossing of coins, or throwing of a dice, or throwing a dice, or etc., and observe their outcomes. You will now learn to measure the chance of occurrence of a particular outcome in an experiment. So what we want to do, we want to, for example, the kind of experiments that are very popular here are, for example, tossing a coin, or, for example, throwing a dice, or so on and so forth. Such experiments. And these experiments are particularly important and popular here because, for example, when you toss a coin, you could get either heads or tails. But for example, it's not when you throw dice, you could get either a 1, or you could get a 2, or you could get a 3, or a 4, or a 5, or a 6. So you have basically these possible outcomes, these 6 possible outcomes, when you throw a dice, or when you toss a coin, you have only these two possible outcomes. Now what we want to do here is we want to learn how to measure the chance of occurrence of a particular outcome, in an experiment. And just to make sure that you understand what this means, is that we want to learn how to measure. Measure meaning that you want to express basically those outcomes in terms of a number. Now the chance of occurrence of a particular outcome, meaning that how likely it is that a particular outcome occurs, and what an outcome is, basically, for example, having heads would be an outcome in tossing a coin. Having basically tails, or getting tails, would be another possible outcome in tossing a coin. And when you toss a coin, you're doing an experiment. So you're doing an experiment, you have these two outcomes, and you want to learn how to measure the chance of occurrence of any of these two particular outcomes when you do that experiment. So now, as some history of probability, it says that the concept of probability developed in a very strange manner in 1654. A gambler, Chevalier de Mere or something like that, some French guy, I suppose, approached the well-known 17th century French philosopher and mathematician Pascal regarding certain dice problems. So there was some guy who was a gambler, and he wanted to, most probably, to win, right? Okay, so now this gambler goes to the French philosopher and mathematician Pascal regarding some dice problems. Most probably he wanted to win, because that's what gamblers would want to do, really, of course, most of the time. And Pascal became interested in these problems, studied them and discussed them with another French mathematician, Pierre de Fermat. Pierre de Fermat was also a popular and a famous mathematician, who has done many sorts of interesting and important things in mathematics. So it seems that Pascal went to basically disclose the problem to Fermat, and both Pascal and Fermat solved the problems independently. So both of them independently worked on the problems, and they solved the problems. The problem, basically. This work was the beginning of probability theory. So there is something called the probability. This is not an easy word. Probability theory. So this was basically the beginning of the probability theory, meaning that the probability theory is actually a thing, you could say. Now, the first book on the subject was written by the Italian mathematician J. Cardan in 1501, who lived basically from 1501 to 1576, and the title of the book was Book on Games of Chance. The Book on Games of Chance, which was published in 1663. And then notable contributions were also made by mathematicians J. Bernoulli. Bernoulli, I think he was German, who lived from 1654. So J. Bernoulli, 1654 to 1705. So these were also the contributors. There was some contribution made by P. Laplace. I'm not sure I'm pronouncing the word right. Let me see if well, in college they used to pronounce these words Laplace. Well, the problem is that in college in India, they pronounce everything completely differently. So when you attend mathematics classes, they pronounce everything well, their own way. And of course, for example, any word, for example, glass is a word. In different, basically, for example, in North American English, it's pronounced in a certain way. In for example, British English, it's pronounced in a different way. In Australian English, it's pronounced in a different way, and so on. There is no problem with that. You can even come up with your own way of pronouncing the word as long as people understand you, and that would be no problem. But when it comes to names, a name you cannot, and you shouldn't really, you shouldn't just pronounce it in any way that you want, because it's the name of a person. The name of the person has to be pronounced the way that his name would actually be pronounced in his own, basically in his own country, in his own language, and so on and so forth. But this kind of thing is not really done in India. For example, in India they pronounce this word as Laplace. But as we heard here, it seems that the word is actually Laplace. So anyway, P. Laplace, 1749 to 1827. 1827, he was also a contributor. There was also another computer, A. Markov, or whatever that is. Markov, 1856 to 1922. There was another contributor, A.N. Kolmogorov, or whatever that is. Kolmogorov, who was born in 1903. So that's basically, these were the contributors, but it seems that primarily the work was developed by Pierre de Fermat. Primarily the probability theory was developed by Pierre de Fermat, and who was a French mathematician, and Pascal. So the name is Blaise Pascal. I would want to know how to pronounce this word, but it's not really that important right now. Okay, so now that was some history of basically the theory of probability. Now as an activity, what we want to do is that take any coin you want to take any coin and toss it 10 times. So you want to toss a coin and 10 times. Toss a coin 10 times. And you want to note down the number of times you get tails, the number of times you get heads. And you would record, you could record your observations. For example, you could record your observations in a table. For example, the number of times the coin is tossed, the number of times you get heads, the number of times you get tails. And so then what you can do, suppose that you come up with some data in this, basically in this experiment. For example, you have the number of times the coin is tossed, the number of times the coin is tossed, and then you have the number of times you get heads and the number of times you get tails. And then, for example, assuming that you toss the coin 10 times, you get some, basically a number of times you get heads and the number of times you get tails. And then what you want to do, now I'm not basically, there is, I mean, when you toss a coin 10 times, of course, I haven't done the experiment myself. I could do the experiment. I haven't done the experiment myself, but it seems that based on what I have read, you would get, for example, something like six times, for example, tails, and for example, 4 times heads. Or you would get, for example, 4 times heads, 6 times tails, or something like that. It's hard to get, for example, it's hard to get 5 times tails and 5 times heads. It's not possible to get exactly half of the time tails and half of the time heads, if provided that you toss the coin for 10 times. Now, I mean, both of these numbers would somehow converge towards basically 5, half of the total number of times that you toss the coin. But if you toss the coin 10 times, you don't quite get to 5 if the number is so low. Now, if you increase this number, for example, to 100 times, then this number converges more towards the half of the number of times that you toss the coin. And again, if you increase this number, then this number seems to be converging more towards the half of the total number of times that you toss a coin, and so on and so forth. But for now, let's just go with the experiment and see what happens. And for now, basically what's important here is that basically the number of times that you get, for example, heads, and if I take this value, for example, as A, if I divide heads by A, and if I divide tails, let me take this number as, H, variable H, or in lowercase h. Take this as lowercase h, take this as lowercase t. Now if I take the number of times that I get heads and divide it by the total number of times that I toss the coin, and also if I take the number of times that I get tails and divide it by the total number of times that I toss the coin, so I get basically these two fractions. in these two fractions, the denominator, as you can see, is in both cases the total number of times that I toss the coin. In one of the cases, the numerator is the number of times that I get heads, meaning one of the possible outcomes. And in the other case, the numerator is basically the number of times that I get tails, or in other words, the other possible outcome of this experiment, which is tossing a coin. Now this is important, and you need to pay attention to how this goes. Of course, I wish I did have a way to explain this through, but for now we cannot explain this through. In the end of these two chapters, when we're done with the review, then we can hopefully merge everything together and explain everything, put everything together and explain everything in a better way. But for now we need to go step by step. Now number two, the second part of the experiment is toss the coin. Now this time you want to toss the coin 20 times. And in the same way, again, record your observations. And again, find the values of these two fractions. And again, repeat the same experiment by increasing the number of tosses, meaning that you keep increasing this number. And record the number of, and again, basically record your observations and calculate calculate these two fractions, right? And what you will find here, as I mentioned, and this is not based on what I have personally done, but based on what I have read in these two chapters, basically. So you will find that as the number of tosses gets larger and larger, the values of the fractions come closer to 0.5, meaning 5/10, 5 out of 10 and 5 out of 10. To record what happens in more and more tosses, the following group activity can also be performed. Okay, so we have another activity here. So basically what we learn here is that, well, of course, only probably theoretically what we learn here is that as you increase the number of tosses, these two fractions tend to the values 0.5 and 0.5. And it might be interesting to note that basically 0.5 is the same thing as, well, 5/10. And if I divide this by 5, I'll get 1. If I divide this by 5, I'll get 2. So 5/10 is the same thing as 1/2. And in this experiment, as you can see, this 2 would or might correspond to the total number of the possible outcomes of the experiment. And this number corresponds to the number of the specific outcome under study. Meaning that, for example, in this case, what we have over here is the numerator is the number of times that I'm getting tails, and there is only one way of getting tails. So this is the 1. There is only one way of getting tails. And this 2 corresponds to the total number of possible outcomes of the experiment, which is either the possible outcomes of the experiment could be either tails or heads. So this basically this corresponds to basically the total possible number of outcomes of the experiment, which would be, for example, tails or heads, and this number would correspond to the number of specific outcome that we are interested in. For example, we are interested in knowing the possibility or the probability of heads coming up. So that would be 1 to 2. And then we are also interested in knowing the probability of tails, for example, coming up. That would again be 1 to 2. That means that the probability of getting I mean, informally, I would say, you could say that the probability of getting tails is basically 1 to 2, and also the probability of getting heads is basically 1 to 2. Because, and the reason for that is that basically and the reason for that is that when I'm talking about tails basically can be represented only by basically one possible outcome. So that's your 1. And heads can also be presented or represented with only one possible outcome, which is basically this 1 over here, this 1 over here, this 1 over here. And so the denominator of these two basically fractions are basically the total number of the possible outcomes that might occur in this experiment. Meaning that in this experiment it's possible to get heads, tails, and so the number of them, if you add them together, that would be simply 2. That's basically why you have a 2 over here. So that's basically the whole concept of probability. Now let's go through the second experiment or the second activity here, see if there is anything over here to note, and then we will move to the next things. Okay, so activity number 2, of course I'm coming at these lessons from a different perspective. These activities are supposed to be actually activities, but I'm reviewing these chapters, and so I'm just jumping into some conclusions, and hopefully my conclusions are right. Let's see if that's the case, but then activity 2 is divide the class into groups of 2 or 3 students. Let a student in each group toss a coin 15 times. Another student in each group should record the observations regarding heads or tails. Note that the coins of the same denomination should be used in all the groups. It will be treated as if only one coin has been tossed by all the groups. Now on the blackboard, make a table like table 15.2, and first group 1 can write down its observations and calculate the resulting fractions. Then group 2 can write down its observations but will calculate the fractions for the combined data of the groups 1 and 2, and so on. So what that means is that it's actually interesting. We may call these fractions as cumulative fractions. We have noted the first 3 rows based on the observations given by one class of students. So what you have here is basically a table, which I will show you here. So this table is basically what it does, what it means is that you have this group 1, 2, 3, and so on and so forth. And the number of heads was, for example, here 3, the number of tails was 12. So that means that the coin was tossed 15 times in total. So that means that the total number of times the coin is tossed is the total number of times the coin is tossed and the total number of times the coin is tossed. Oh, I'm sorry, this is a fraction. This is the cumulative number of heads and the cumulative number of tails divided by the total number of times the coin is tossed. So for example, over here you have 15, and as the total number of times the coin is tossed, the coin is tossed, the coin is tossed, and over here you have the total number of times the coin is tossed, 15 times. So that's 3 to 15 and 12 to 15. Over here you have basically so over here you can add these numbers together, 3 plus 7, and again you have tossed the coin another 15 number of times, so 15 plus 15, and that, so over here you can see that your number is 3 to 15, which is 1/15. Over here the number goes 10 to 30, which is 1/3. So 1 to 15 is basically some number like 1 to 15 is some number like 0.06, 666, and so on and so forth. Now 1/3 is some number like 0.33333. And then 17 to 45, for example, yes, 17 to 45 is some number like 0.3777, and so on and so forth. And so as you can see, the numbers are getting bigger and bigger, but they will most probably tend to some number. Let's see where this thing goes. You will find that the total number of tosses of the coins increases. You will find that as the total number of tosses of the coins increases, the value of the fractions in column 4 and 5 come nearer to 0.5. So over here we had, for example, 0.3, 0.4, and you can just keep going. The total number, the numbers are tending to 0.5. So that's another thing that you can observe about this activity as well. And over here we are calculating the cumulative number of heads, meaning that we are putting together different observations by different groups, but we are assuming that the same coin is being used in all of those observations, or in all of those activities, in all of those experiments. Now, as another activity, we want to throw a dice 20 times, and note down the number of times the number 1, 2, 3, 4, 5 come up, and record, and we want to record our observations in the form of a table, as some table over here. So for example, if you throw a dice is also an interesting is an interesting experiment. So you have the number of times that the dice is thrown, the total number of times the dice is thrown, and then based on that, basically you could have the total number of times these scores come up. So the total number of times these come up. And what that is, for example, you could have 1, 2, 3, 4, 5, and 6. And then you can record all of those observations. you can record all of those observations. Right, so you can record all of these observations over here, and for example, you can what you can do here is that you can record for example the number of times 1 turns up. The number of times 1 turns up, I denote that as A, and the total number of times that the dice is thrown is, let's take that as H. So for example, you can calculate A by H. If you take this as B, C, D, E, F, for example, then you can calculate B by H, you can calculate C by H, you can calculate D by H, D by H, you can calculate E by H, you can calculate F by H. And of course you can see that basically A, B, C, D, E, F is basically, that denotes only one possible outcome out of, for example, 6 possible outcomes, because you have 6 possible outcomes here. You could get either a 1, a 2, a 3, or 4, a 5, a 6 over here. So you have 6 possible outcomes. 1, 2, 3, 4, 5, 6. I don't mean that the numbers themselves, but the possible number of outcomes, or the possible, basically the number of these numbers, which is 1, 2, 3, 4, 5, 6 numbers I have over here. So you could have either this outcome, or 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 this outcome, which is 6 possible outcomes. So your H could be 6, or your H is actually 6. Now the number of times A comes, the number of times 1 comes up is recorded, is denoted as A. The number of times 2 comes up is denoted as B. The number of times 3 comes up is denoted as C. The number of times 4 comes up is denoted as D, and so on and so forth. So then you can say that the probability of one, basically of 1 coming up would be 1 divided by 1 divided, or basically A divided by H. The probability of 2 coming up would be B divided by H. The probability of 3 coming up would be C divided by H, and so on and so forth. And then you're supposed to throw the dice 40 times, record the observations, and calculate the fractions as we did here. And as the number of throws of dice increases, you will find that the value of each of the fractions, of each of these fractions, calculated, comes closer to, they just keep tending to 1/6. This would tend to 1/6, and so on and so forth. It means that, and this 1 denotes basically that the total number of ways that 1 can be represented, which is only 1 time in this dice experiment. The total number of times that, for example, 2 can be represented, or the total number of times that 2 can actually happen, is basically 1 time, because there is no other way of representing 2 on a dice. The total number of times that 3 can be represented on a dice is only 1 time, and so on and so forth. And the total number of times that the dice is thrown, or actually the total number of possibilities that can come up here in this scenario, is basically 6 possible outcomes, which is either a 1 or a 2 or a 3 or a 5 or a 4 or a 5 or a 6. Other than that, you can have no other outcomes. Meaning that when you actually throw a dice, there are only 6 possibilities. You will either get a 1 or get a 2 or get a 3 or a 4 or a 5 or a 6. There is no other possibility. So you have, in total, you have six possible, or you have basically 6 possibilities. So that's basically what is represented by this number. And then as you increase the number of times that you throw your dice, of course this h is not the total number of times that the dice is thrown. That's not actually right. But hopefully you get the meaning, or my meaning basically. So as you keep increasing the number of times, the total number of times that you throw the dice, each of these fractions keep tending towards 1/6, 1/6, 1/6, and so on and so forth. So, and that's of course the kind of experiment that you need to do, for example, for 1,000 times or 2,000 times or 3,000 times and so on and so forth. And then in higher mathematics we will actually use limits in order to basically study this kind of thing. But for here and now, we have to just keep doing that experiment 1,000 number of times, 2,000 number of times, 3,000 number of times, and actually do that practically in order to get a sense for that number, which is of course not possible. That's why we are talking about the theory here. So it says that to see this, you could perform a group activity as done in activity 2. Divide the students in your class into small groups, meaning that you can take a larger number of people and keep doing the same thing, and then calculate the cumulative number of things as we did in the previous example. And observations should be noted and cumulative fractions should be calculated, and the value of the fractions for the number 1 can be recorded in table 15.4. This table can be extended to write down fractions for the other numbers also, or other tables of the same kind can be created for other numbers. So for example, you can have 1 group, 2 groups, 3 groups, 4 groups, and so on and so forth, and then you can basically have the total number of times a dice is thrown in a group, and then you can record the cumulative number of times one, for example, turns up, divided by the total number of times the dice is thrown, and then basically keep calculating that fraction cumulatively, and then you will see that your numbers will tend to 1/6, 1/6, and so on and so forth. And the important thing here is that the dice used in all the groups should be almost the same in size and appearance, meaning that we are actually assuming that we are using the same dice, literally the same dice in all of these experiments. Of course, the same dice cannot exist in nature, meaning that even if you create the same, basically 2 dice, the exact same size and the exact same dimensions and the exact same everything, that those would still be 2 different dice, right? But for the sake of simplicity, and because we do need to assume certain things, what we need to do our best to create, basically, for example, if we have 6 groups over here, and if we want to do things cumulatively, which is of course the best thing to do in such cases, then what you need to do is that, for example, manufacture the same dice with the same dimensions, the same size, the same weight, the same everything. Of course, there are many sorts of considerations when it comes to creating the same dice, of course. but then we will do our best to create the same dice here and then distribute those dice to basically the different groups that we have, and then keep performing the experimentation cumulatively, and then put all of data together. And as you can see, of course, we will, if you keep increasing, for example, the number of groups or the number of times that each group is performing the same experiment, you would come up with a whole amount of data. And that whole amount of data, you need to find a way to deal with that. So in order to deal with that large amount of data, you need to have a way to do that. So in order to do that, what you can do is that you can use statistics. And that's basically what I meant by using statistics in probability. Anyway, so it says that the dice used in all the groups should be almost the same in size and appearance, and then all the throws will be treated as throws of the same dice. And then if that's the case, which involves basically a whole number of assumptions that you need to make. For example, when you throw a dice, you're throwing a dice on, for example, some surface. No two surfaces, if you get into the physics of things, no two surfaces are the same. Meaning that even if you are talking about the same, basically tabletop, for example, when it comes to, suppose that you have this tabletop over here, right? I should not really talk about all of these things here, but, well, as long as we are talking about them, let's talk about them. So suppose that we have all of these groups performing these experiments on this tabletop. Now on this tabletop, let's say that this is a tabletop. This whole thing is a tabletop over here. Now, if I have this tabletop over here, let's say that this is group 1, this is group 2, this is group 3, this is group 4, and so on and so forth. And all of these groups are performing these experiments on these areas of the tabletop. The same tabletop, really. But again, if you get down to the physics of things, then in order to be able to do things cumulatively and put all of your observations together cumulatively, you need to basically treat the whole tabletop as one surface, having completely the same kind of characteristics, which is not true, because this area of the tabletop would be different from this area of the tabletop, would be different from this area, and so on and so forth, because of all of the forces and and the molecules and the atoms and the electrons and everything that are involved. But we are assuming that the whole tabletop is a surface, for example, basically is a united surface that has the exact same type of properties. So then based on that, you are basically doing that experiment, doing all of the, for example, 8 groups are doing the same experiment on the same tabletop in their own designated areas, and then we will put together all of the data related to those experiments. We treat them cumulatively, and then based on that, and then of course we have the dice over here. The dice, we have basically, supposing that we have 8 dice given to the 8 groups, for example, the 8 dice are treated as just one single dice, which is naturally not possible. But we are going to do our best to manufacture the same dice with the exact same properties, everything, and then we will manufacture those dice and give them to the 8 groups, and then have them basically do the experiment on the designated area, and then we will record our data, and that will be basically the cumulative result of all of the experiments put together cumulatively. So that's the whole story. Of course, I'm not talking about probability, I mean basic probability, but I'm giving you all that I know, or all that I can talk about in this particular case. But I hope that you can that you understand basically the whole story here, and then we will just keep going forward. We will have different situations, and let's see where that takes us. So I'll see you in the next video, and thank you.